The next amino acid to talk about is glutamic acid. I'm here on the glutamic acid page to start because the first thing to talk about is that it's sometimes called glutamate. So if it's an ionized version, it's called glutamate instead of glutamic acid, but it's the same thing. So now jumping to the amino acid page, you can see here in the list glutamate as the number 6 item on the list, sorted by abundance in proteins. Go ahead and draw it here. Alpha carbon, carboxyl group here. Amino group. Okay, so glutamic acid, as you guessed, is an acid. So it's going to be the same carboxylic acid that we've been seeing on every amino acid, just on the side chain this time. Let me finish drawing it real quick. Okay, so that's glutamic acid, and if we were to take away that hydrogen, give it a negative charge because we lost this proton because it's an acid, and now it's glutamate, the negatively charged version of glutamic acid. So I've already searched for L-glutamate. You can see that on the side here, N-terminus, C-terminus, side chain coming out towards us because it's left-handed version. So you can see, let me draw the hydrogens on this. You can see a couple of carbons in the chain before you get to the carboxyl group at the end. And it's showing a hydrogen here, but at cellular pH, that hydrogen is going to dissociate, and the molecule acts as an acid and becomes the conjugate base glutamate. So there's this proteinogenic amino acid page on Wikipedia. So these are just the normal amino acids we've been talking about. They are ones that get incorporated biosynthetically into proteins during translation from messenger RNA into proteins. But there's some useful information on this page that's not on the amino acid page. So you can see here, these are all the amino acids, and we're talking about glutamic acid here. The abbreviation is GLU for glutamic acid, which makes sense, but we've already used G for glycine, and so we can't use that as a single letter. And I believe that since aspartic acid and glutamic acid are similar, they just went with D and E to describe them, since they're right next to each other alphabetically, and the molecules are similar to each other. So if I just take some time to get used to E glutamic acid, it might actually be easier to think of E as glutamate. At least there's an E in glutamate, where there's no E in glutamic acid. I didn't talk about pKa before. But you can see here pKa 4.2. So if glutamic acid was floating around in some environment of pH 4.2, you'd expect roughly half of the glutamic acids to be protonated and half to be deprotonated. So you'd expect half to be glutamate and half to be glutamic acid. So there'd be kind of it would be an equilibrium where you'd be removing the hydrogen, adding the hydrogen in equal amounts, so half your molecules are in one state, half the molecules are in the other state. Sorry about that. Finding where I was at. So if you're in an environment of 4.2 pH, that would be the case, half and half. But cells are 7 something pH usually. So that's going to be a more basic environment. So there'll be kind of a lack of free hydrogen ions in the solution. And because of that, it's more likely that glutamic acid would lose its hydrogen to the environment and not be replaced as readily. So in a cellular pH environment, you're more often going to see the ionized form of the molecule. Hopefully that makes sense. And the pKa value kind of gives you the threshold where you'd go from a 50-50 mix. On the same page, proteinogenic amino acids. It gives a nice little description of each one. So glutamic acid behaves similarly to aspartic acid and has a longer, slightly more flexible side chain. We won't talk about aspartic acid until we get to it, but just know that the side chain here is slightly longer than aspartic acid. And I guess the main thing to know is it's negatively charged. So before we were dealing with hydrophobic molecules and polar molecules, and this is actually a -1 charged side chain. Still on the same page, just a different table. So we were looking at the amino acids sorted by abundance. On this page, you can actually sort by abundance in eukaryotes. And I was claiming before that they were the same, but they're not. So the first most abundant amino acid is leucine, but the second is serine. So we cover them in a slightly different order. Glutamic acid would be 4th on the list, whereas we're covering it 6th on the list. I guess just to know that this nice table here is available to sort by amino acids, so you can actually see a more detailed view of their abundances. It might be from a slightly different set of proteins that they're looking at compared to that original study on the reference from the amino acids webpage, but I'm not sure. Also, nice to see this list of which ones are essential and non-essential. Speaking of which, glutamic acid is non-essential, so there is a way for the human body to make it from something else. Probably don't need to mention this, but I did talk about codons last time, so you can see that there's 2 codons that can be used. 2 codons that during translation signify glutamic acid should be the amino acid. Glutamic acid was named after gluten. So they treated gluten with sulfuric acid as part of the way they discovered this amino acid. And I think that's pretty much everything I was going to say, but I should have mentioned this in the summary video maybe. So since it's negatively charged, it's called an anion. When glutamate, it's called an anion, and also the name changes to glutamate. But I just wanted to point out that an anion, the "an" prefix is a Greek word for up, and it comes up in a variety of contexts. So anion is up an electron, meaning it's negatively charged, which is a little confusing, but you just have to remember to think like electrons. You have a neutral atom, you go up in electrons, you become negatively charged, you become an anion. Same with anabolic. You're going up, you're building molecules in an anabolic process. Cat means down, catabolic, you're breaking down a molecule. Cation, you went down an electron, which means you're positively charged.